So the first question was asking for the permutation relation. And I was a little surprised, but these all was the homework problems, so, but it still did not work that out. So any particular question you want me to go over? Any particular question you want me to go over? Any one of them want me to go over? I can go over any one because we have a total 3 on those problems. Could you double check which one you want me to go over?
First one.
First one? Okay, very good. So I will go over first one. Just make sure you understand how this is calculated. It's quite important. First one, we have 2 of these. So the first problem here is that we have 2 commutator essentially. Is it x px squared or is it x squared or px squared? Is it x squared?
Px squared.
Px squared. All right, very good. That's px squared. Okay. All right, px squared. Now, when you have these known commutator like this, so you need to be careful in the sense that, for instance, in exams, we definitely will quiz you guys on like this. So here is the commutator px hat like this. If you have a commutator like this, don't try to add a function because we can use the rule, as we said it before, A, B, C like this. We can use this rule to expand it. Okay, so essentially you would have A, B, and C in the back, and B in the front, coding with me so far. So in other words, you're going to have an A, B, and C in the back, and then C in the front. So you're going to see me write down px and x hat px and a plus x px like this. And then all you need to do is just px this x px, this is just ih bar like this. So that's it. And then you have twice that. That's why you get that one here. Okay. Are we good? So, and that's how to do the calculation. Second one, you definitely need to use a function. Auxiliary function for the second one. Second one, you can see it's the eikx px have like this. So here you have to use auxiliary function because there's no known expression you can use. If you know that expression, you can use it. But if it's not, you have to do like put an f in the end and solve for it. Okay. And you can see my solution there so directly. So that's all you need. Any other particular problem you are interested in for me to explain it?
Can we look at A and B of number 3?
Number 3, A and B. Okay, let's do A and B. All right. I was really surprised. It asked you write down a Hamiltonian for harmonic oscillator. Look, take a look at this. So this harmonic oscillator, it just equals A dagger A plus 1/2 h bar omega. Hamiltonian. That's a Hamiltonian.
Yeah, I can remember it at the moment.
Really?
Yeah.
Okay, well, you do need to remember now. So, and that's the expression which we have. And this is exactly the same thing as we did. This exact same thing if you write a px, you know, a whole bunch of things. Exact the same like this. So they are exact the same. So these two are exact the same. We explained last time. And then eigenenergy, just replace this n, A dagger n by n. So this will be eigenenergy. So you need 2 minutes to get this out. All right. Not that complicated. So that's all you need. That's it. So this is A and B. C, proof. Again, this is the homework problem. If you cannot do it, this means you don't understand fully yet. Make sure double check your calculation, and hopefully you will be able to understand that one. So this is one that I have. Any other questions you are interested in? Any other questions? In my solution, the A dagger, I did not provide them, I think for some reason, yes. But the direct calculation can be done exactly the same way. You would just plug in the operators. So you plug in two operators, we have an operator there with 2m h bar omega like this. And then I look at some of your work. It's a really expensive work, but the key idea here is that you put a comma in between these two, and you have two terms. Let's call it first term, let's call it A. Second term called B, like this. So that's basically these terms. And the second term here, this A dagger should be minus sign. So like this. And then you will have 4 commutators, which is correct. You see, you have A commutator, B commutator. These are all zeros. So A 0, B 0. You will have A non-zero. Just add them up, you will get 1. You got it? Okay, all right. The last one, again, homework problems. The bonus to the exam, number 1. So this will be the bonus I explained many times in class. The solution already in my notes. Sounds good? Sounds good? What do you think? What do you think? What do you want to do? So here's what I propose. Since not everybody got good grades, and here's what I propose. You know the keys. Every key, you know the keys. And after the spring break, I allowed you to redo the whole things again without any key in front of you. And you can sit in the room like this after first Monday's class after spring break, and sit here and you work that out. And I gave you 50% points, whatever you will get. And you will, that 50% points will replace whatever your current grades is. And this also applies to the D, which is the to the 20 points bonus. But here's one catch, because we already know ground state. And your job is calculating. I want to make things a little more exciting, or more slightly complicated, because did you see we got already 5-0, right? We're going to get a fair 0. So your job is try to find this guy. 5-1, okay? From 5-0, 5-1. So anyone are interested in and still interested in, you can work on that. Okay, so you basically can do it like that. So this will I give you again at the minimum 10 points. I will give that to you. Okay. Anybody else has questions on this? So again, this will be exactly the same thing, except that you can work that out in separate. Sounds good? Sounds good? Sounds good? Okay. Make sure you do turn in the homework, and we're going to collect homework whenever you're ready. Okay, so this is a quiz, and make sure you really take seriously, because after the spring break, the points we have is gradually decreased, because we're almost past the half point. It's really serious. Okay, you need to catch up right away. All right, now let me show you another screen here, which I'm going to ask you guys some questions about the last class. Let me remind this. I don't need this. I don't need this either. So let me see that. The question that I'm going to ask you guys. There it is. Here, and I'm going to share the screen, and we'll ask you some questions about this. All right, you guys should be ready. Let me show you. This is March. This already done with that. Table homework. Okay, so now we did a review of the quiz,
And these ones we already did it. And the quiz already. Okay. So review the last class. Now I'm going to. First question to Cody. Why does A look like a matrix in the representation of eigenstate of harmonic oscillator? Why does it look like a matrix? So we have A, why it could become a matrix? Any ideas?
Toby, can you help? The diagonal terms are 0, so it's only when the wave functions are the same that you get a term that goes across.
Yes. So the correct answer is because the operator themselves, they are matrices. Operator themselves, they are matrices. Operators are matrices. It's just representation. In the Schrodinger representation, these A dagger A is like these unit px plus x like these and relate to that. That's the Schrodinger representation. But in the Heisenberg representation, everything is just a matrix. Because we use the basis functions as a harmonic oscillator, so that's the main reason. Okay, so just remember, the answer to this is because all the operators are actual matrices. So that's what we want. All right. What are the key differences between the Heisenberg and the Schrodinger pictures?
Schrodinger's equation, when it's t equals 0, and t equals 0 does not equal when it's t not 0. And in Heisenberg, it does. And it flips around for, what's A?
For the A, what is A?
Just an operator.
Exactly. Good job. You got it? Everyone got it? So that's the main reason. Okay, cool. So that's all that I have a question for. And I do not need this anymore now. So bye-bye. Close this guy here. Stop sharing. So I don't need it. So yeah. So today we are going to move on to the Schrodinger, the Heisenberg equation of motion. And that's where we're going to start. So we already put down something here. So that is, here's Heisenberg principles, so which we're going to continue on this part. So now I'm going to move on to this part, and we already gave you some guidelines on what will happen. And today we're going to move on to the real equations, and you're going to see them clearly. So remember, here's a one-to-one correspondence between these two relations. So that's we are going to learn this part. Okay. So this is the one which we stopped last time. Again, Schrodinger picture, we use S. Heisenberg picture, we use H. And these are how the wave functions all relate to each other. Before I move to the equation of motion, and I'm going to show you connections between these two. Between S and H. So I want to make, they are connected. They're not just separate. They are not separate. They are actually connected to each other. So that is why I'm going to show you how these two are related to each other. So they are related to each other in the sense for the wave function. This is the wave functions. They relate to each other for the wave functions. Only at t equals 0 they are related to each other. So phi sub s t equals 0 equals phi sub h t equals 0. In other words, the initial wave function, regardless which picture you are in, they are exactly the same. Similar for the operators. For the operators, they're also the same. T
equals 0, of course, this doesn't matter whether it's equals 0 or not equals 0. This equals, and, beginning. A hat as the Schrodinger picture, and here's also A hat Heisenberg picture, t equals 0. So these two are related to through the initial conditions for the wave functions as well as the operator. So these are the differences. Now I'm going to move on to the equation of a motion, and we're going to show you how do we use them and what's the trick which is involved, and that is my second item. So this time we are going to talk about the equation itself. So now we're going to start with the equation. So let's get started with the equation. So this is the equation of motion. So equation of motion is quite important, and these are the four operators. They're not for the wave function, for the operators, not for the wave functions. And for this reason, it has many benefits. And so the first of all, on the left-hand side, we also have RH bar. But now, the operator, we have full derivative of d, dt, and the operator like this. And this is different from a Schrodinger equation. Schrodinger equation here is a partial t, but the Heisenberg picture is a d. So this is one big difference. And then Heisenberg picture on the right-hand side is a commutator, not a Hamiltonian times the wave function. It's commutator times the Hamiltonian. So this A has to add a subscript h here, subscript h here, h here. This all means the Heisenberg picture. So here you must be h everywhere has h in it. And if for some reason the operator itself, the starting operator itself, is dependent on explicit dependent on time, and then you have another partial HA like this comes out. I will explain each part of this clearly to you, what this part means. Here is a comma, forgive me, so that's the commutator. So that's the equation which we are going to use. And let me first explain this relation. First, this part, I call it term number 2 first.
And that goes on the right side?
Yes, it's actually together. Okay. Let me write this down. I just want to make sure camera catch the plus term. Oh, yeah, I do need to move the camera. Just give me a sec. Once I move the camera, it should be able to catch all of them. It should be on the single line. Let me move over here. It should be this on a single line like this. Like this. So this will be term number 2 here. And I want to show you. So usually the number 2 term is not available. Usually it's 0 if the term is that okay, but sometimes do. So this says the operator A is time dependent. Watch carefully. Already in the Schrodinger picture. Here is something a little bit messy. It's not that completely clear. Because some operators may be already time dependent in a Schrodinger picture, but now you run into the problem with that you are saying the operator is not time dependent. You see here, this operator is not time dependent, but eventually you will realize there is a problem with this. So what I said here was that if this A itself already time dependent, which means that in the Schrodinger picture, this relation already the wrong one, so to speak, wrong one, then what do you do with it? So that's the key. So this is what you're going to see. That's why we use a partial here. Let me give you a quick example why this could happen. Suppose I have a light wave like this, just a light wave propagating, and you can see we have an electric field, also have magnetic field V here. Now these guys change with time. Regardless which picture you use, Heisenberg picture change with time, Schrodinger picture change with time. So you're stuck with this. So that's difficult. That's difficult. And but in our chapter, we actually this still time itself, not time dependent. So that's what I mean here. So this is the commutator itself, and we're going to enjoy this one before we show you how do we derive this. So first, folks, we're going to read example on page 70. Oh, sorry, example 80. Forgive me. Actually, I don't know what the page number is. That would be examples 7 and 8. I want you to read these two examples, and I give you 5 minutes to read them. So this part is quite important. Page 70, and let me check. Are you sure? This is just before section 3.6. Just before section 3.6.
Example 7 is free particle.
Yes, free particle example. Do you see it?
Yeah.
Wonderful. Yeah. I'll give you 5 minutes to read them. All right. On page 80. Did I say 80? Yes, I said 80. 5 minutes reading. Make sure you do read them. If you have questions, please let me know. Any questions?
What's the X dot P dot?
Oh, this means great question. Great question. X hat dot equals dEx x hat. It's just operator, derivative operator. So that's, sorry, I did not explain in the book, so that's what it means. Any other questions? Did you guys finish or still working? Yeah, keep on reading until all you do.
So that doesn't mean time dependence? Not dependence, but like a time derivative?
Yeah, it does mean time derivative. It is time derivative. It is time derivative. It's just like the same thing like this. In other words, I can rewrite this whole thing. Just simpler notation, but like this. So this part will be exactly the same. So in other words,
so should the d over dx on the dot be a t?
You mean what do you mean? D over
like over here on the left with the a, how it's d over dt a hat. So for the x, should it be d over dt x hat, or?
In there, if you use the x as a way, and this part will be changed to d dt x hat. This is denoted as like this. Is that what you are asking for?
Yeah.
Okay. So that will be exactly the same thing. So like this way. Okay. Yeah, it's a really great question. Essentially just a simpler notation because you have hat derivative is kind of a little bit harder to write. Any other questions? Yes, go ahead.
So it's just the velocity operator that's being introduced?
Exactly. This is just the velocity.
Okay.
This is the velocity operator. This is the velocity operator. That is classical physics, exactly the same. That's why people initially like Heisenberg vector so well that you basically, if you remove this hat on the top, it's just like classical physics. There's nothing new whatsoever, essentially just classical physics. Did you see that? That's a classical physics. So that makes the entire thing much simpler to understand it. You can see classical physics, and that's the everything's basically a classical way of thinking like this. Any other questions? Any other questions? Yes, Toby.
For standstill, when it talks about needing the wave function to put in the initial conditions, how did you get the e to the ikx over the square root of L? Is the e to the ikx just the wave function of a free particle and then the...
Yes, that's the both box lengths.
Okay.
The box lengths with L. So this is just assuming that if you seal a plane wave in a box with the length L, and then your wave function has to be kx over square root L like this. So in other words, the operator itself does not give you expectation value because you need a wave function in order to get expectation value. But this operator is so beautiful in such a way that it shows the physics really, really well. Any other questions? Any other questions? Cody, no more questions? Okay. Now here I have a question for you. I have a question for you. Position operator, is it equal to 0?
Yes.
Of course, it is equal to 0, right? Because they are same. This equals 0. But the trouble was that when you have time, at a time equals 0, the position operator, at time not equals 0, they are not a commutative at all. The main reason, if you look at the equation in the book, you notice that this guy, x hat of t, and you will notice, which is correctly you see, so you're going to see in the equation you have x hat t0 plus px hat divided by m multiplied by the t. Then if you plug this guy into the equation, which I just showed you there, it won't be equal to 0. So this is the strange behavior, which means in the beginning, the position, they are actually permute, but now when at t not equals 0, they no longer permute. And this is so-called uncertainty, time-dependent uncertainty. Dependent on time, well, you become uncertain. That's what happens here. So this is one of the very important consequences. And so the second example also shows similar behavior, which allows you to do that. And so the week after, we will assign exercise 3.5.2, and you can do the exact same thing. So, and that's how do we use this things to derive it in this way. So this is essentially just show you the equation itself. And now I'm going to show you, let me use this more, I'm going to erase this part, and I'm going to use this part of board. So the next item, and I'm going to show you the key steps. So this is called key steps. So how do you derive the Schrodinger or the Heisenberg equation of motion? How do you get this out from the Schrodinger equation? And that is the key step started here. So key step to, I call it H equation, Heisenberg equation. How to get this one here? And I am going to show you a very simplistic view, but it's quite powerful. Just remember these ones, you will understand how this things do the calculation. The first step of what we do, we introduce an operator called a unitary operator. And a unitary operator, we use a symbol U, put hat on the top. So I want to explain what this unitary means in a second, but I want to show you what it does. What it does. So I just want to explain what it does, why you need these things. Well, what it does something like this. It will, suppose in the beginning you have the state t equal 0, that's a wave function which you have. When you apply that to the unitary operator, it will transform to a wave function t not equal 0. So essentially transform a wave function t equals 0 to a t not equal 0 wave function. So we introduce from the wave function. That is what is doing. And second, the unitary operator is not Hermitian operator. And this is very, very different. It's not Hermitian operator. In other words, U dagger not equals to U. It's not Hermitian. It's not Hermitian operator. You know, it's not Hermitian operator. It's not observable. You cannot observe not Hermitian operator, but it's useful operator for us to use. So then, not equals to U itself. The unitary. So here's the unitary. What the unitary really means is the following: U, the dagger, the Hermitian itself, multiplied by U hat itself equals 1. The unitary, which just means equals 1. So that's what it means. This one is not really number 1, it's actually matrix 1. 1 of 1. Let me use, some textbook use a very heavy bolded 1. This actually all the remaining elements are 0. The diagonal ones just equals 1. If you have this one. So it converts this guy to that one. And so this is the second. So this is the wave function. We will do like this. Second, it's converting the Schrodinger picture, the operator, from this one to the
Heisenberg pictures operator to that, it's going to convert it. This conversion is quite important. I will purposely write in the cellular format. There is one thing which is quite important. So here is the conversion between these two. The permission of the operator, the unitary operator, U multiplied by Schrodinger pictures, the operator, and then multiplied by the unitary operator again. So remember, the operators, when you transform, you always have two of these. The eigenvector, you only have one in this one here. I'm going to use a blue pen to emphasize, a green pen to emphasize. You only once. Here you have twice for operators. Once for wave function. So for the wave functions, U only appears once. For the operator, the U must appear twice. So this is the difference because of this. All right. So, and then when you do the Fourier transformation, and this becomes the Heisenberg picture, and act like this. So these are the key steps after you use. Essentially, when you go from here to there, and that's all the things you're going to learn. Essentially, this is the key. This is the key. If you forget anything that I'm going to talk about later in the next 10 minutes, that's fine. But this part you must remember. In other words, what we are doing here is U operator transform from the wave function in the Schrodinger picture to the Heisenberg picture, and you do the same thing with the operator themselves. Now I'm going to show you a little bit more detailed. Don't be baffled about this, because these are regularly straightforward once you're used to these ones, and I'm going to use the other board to show you the details. And I'm glad that the camera allowed us to catch this part, which is really, really important here. Okay, so now here is the derivation starts. First, we are going to find how this operator works, which I'm going to do now. So this part is the unitary operator itself. I will write some of my notes, and so this is item 4, U operator, so which we are going to on this particular operator. What it does the following. Suppose I have the initial state, let's call it phi 0, at t equals 0, and I say that the U operator, once I apply this operator, it gave me phi t. And I have no information about what does U look like, and I also have no information about this, but I assume this is assumption. So I assume it this way. I always can assume it like that. So what I do, I take the derivative of both sides. I'm going to take the derivative of this side and also take the derivative of this side. So let me show the derivative on this side first. Partial t, U hat aside a t0, and here's a partial t. So they must be the same. There's no question. Yes, go ahead.
So with like how we applied the U dagger U hat to the Schrodinger operator specifically to get it to the Hamilton or the Heisenberg operator. Is it the same idea for the wave functions where we're applying U hat to the Schrodinger wave function to make it equal the Heisenberg?
You are absolutely right. We are on the way to do this. This U operator, since you already eager to know what actually happened, this operator has two indices, two time indices. So when in the beginning, if they are exactly the same, we make t equal t0. They're exactly the same. So this way, we can satisfy the initial condition which I laid out here. Exactly. So that's why the unitary I'm still hiding a lot. I don't want to reveal the whole secret. I just simply say U. Okay, you didn't even know what that U is. I didn't even tell you what U is. You're going to see me to write U has two variables. One's a T, one's a T0. You must be, because this guy's a T in. If this guy does not have a T, then you won't be able to get a T in. So that's the key. Okay, so far so good. There's no magic here. Now, this is a constant. Did you see this side is a constant because the T0 is a constant. So the only thing that I have is partial T U. Put a parenthesis in the front to just mean that there is no derivative. And this part is just partial T. Folks, leave some space in the front. Leave some space in the front. So leave some space in front. Now, once I leave some space in front, folks, I'm going to inject IH bar. Sorry, my font size is a little too small. That's IH bar here. And here's also IH bar. So the left-hand side I have IH bar, right-hand side IH bar. Now, this part from here to there, it's just plug in the Schrodinger equation. And this, of course, just equals the Schrodinger equation. From here to there, it's a Schrodinger equation. Makes sense? Because this is that's a time-dependent Schrodinger equation equals that one. So this is the time-dependent SE. I didn't do anything. I just plugged that into it. So once I plug that into it, so then you will notice that that's the entire equation that I have here. So essentially this part, now you see I can get a U out, but I need to replace this U of psi T. So this is the Schrodinger equation. Now let's move on further. I really like these arrows. That would be much better to explain it, so you can see what I'm doing here. Okay. So this is one that I have. All right. Now, did you see my phi sub t, 5t equals mu, U times 5t. So I'm going to plug that into this relation. So I will get H U hat phi of t, like this. So did you see? I replace this with my assumed ones, and I get this expression. So I make this part looks a little bit nicer, and then we'll be on my next page. Yes, I do have next page. So I would equal, I just copied this from here, phi U T U hat phi 0 equal this. So they must be equal to each other. Because U of T0 is arbitrary. I didn't assume anything, it's just arbitrary. So I can remove this part completely because this is the same thing that we do the commutator. You remember we put an arbitrary function in the auxiliary function in the back. So these two can be cancelled out. So then in the operator form, I would have, you have all look like this. So that's the expression we have. Now essentially, if we solve for U, once we get H, we get a U. So if we have a H, we get a U like this. So that's basically, that's end. When we calculate it. Of course, everybody is eager to know what actually this you can do with it. Let me show you a simpler possible case for you to see them. So in other words, how do you actually use this one here? I'm going to use the simplest possible, and you will see it's kind of a really amazing things, what you're going to see them. I will use extremely simple case, and I'm going to simple example. And I'm going to use one by one matrix. One by one matrix is just a number, right? One by one matrix is just a number. And let's pretend to that way. Because a one by one matrix, let's just put the H becomes a number, let's call it E. Remember, original operator one by one matrix is just one number. Let's put this as E there. And U itself originally is a one by one matrix. It's just a U itself. Okay, so that will be U like this. I just show you an example. I'm going to plug it in and see what they look like. H, mu, U. In the beginning, it's all operated because it's in the one by one, so let's E, U like this. So that's what we'll get. And we can solve this immediately. Partial U over partial U over U. And capital U here equals E to the negative I H bar partial T, like this. So that's I solve for that. And then again, left-hand side is just logarithmic of U. The right-hand side, just E to the negative I E T H bar. So you can see my U just have a U0 E to the negative I E T H bar. Over like this. Have you ever seen this factor? Have you ever seen this factor before? Have you ever seen this factor E to the negative I T H bar over H bar? You do, right? That's a stationary state evolution. You remember stationary state evolution. That's this phase factor comes out. In other words, you remember at the beginning, let's say if you have two eigenstates, when the T phi 1 plus E to the negative I E2 T H bar phi 2. In other words, what we are doing here, sorry, I trick you guys to think it's too complicated. Folks, this unit operator is just a coefficient of the time evolution portion of that. Time evolution portion of that. If in more states, does it make sense to you? I thought about this, how is the easiest way to represent this? Well, we like this, but I did not tell you our U actually this is just our U. Our U here, exactly same our U. Same thing, there's no other magic involved. The only thing that I made assumption was just a single one by one matrix. But if it's not a one by one matrix, it will becomes a little bit harder to calculate on the board. But the same idea. There's no other things involved, just same idea. Sounds good? I'm going to stop here, and I just showed you how you get this U. And once we come back from spring break, and we're going to continue following steps and until we get an expression for the operator that I showed you over there, and that's final results. And this probably takes about 30, maybe 20 minutes maximum. So we will start a new chapter, chapter number 4, hydrogen atom. Starting from the hydrogen atom part, I want you guys to pre-read the chapters now. Because that will real massive. Can you guys promise to pre-read them? Okay, give me a thumb up. Okay. So I will, yes?
Can you send this announcement out like with page numbers?
Yes, I will send you the page numbers, and I want to emphasize. Plus, I will send you another announcement for this particular chapter. And I believe some of you do need an extra credit points in order to pass this class. I worry some of you won't be able to pass this class. So I have 2 assignments. One is, could you guys turn the page? Oh yeah, I can do it here right now. Folks, follow me. Did you see section 3.6? I'm not sure which page I show on your page. What's the page number of yours? 50, okay. So this should be 81. In our book, it's 81. Page 81, the black body radiation. And I want you to read black body radiation and explain how quantum mechanics explain it. The black body radiation, that's number 1. Number 2, could you go to page 86, section 3.7? That photoelectric effect. And here, I want you to read them. Also, this is from our book, and you can, from our actual labs. Did you guys do the photoelectric effect?
Yes.
So this is the experiment, so I want you to read them also. All the data was measured by one of our, maybe 2 students. The original data is actually just our students here. and did the measurement. I think this will be very, very valuable. And keep on going. So the question that once you guys read it, and I want you guys to write a short, maybe 2 paragraphs to explain whether you understand, and I'll give you some credit for that as well. Okay. So this is for the chapter 3. Sounds good? Sounds good? Okay. Chapter 4. Now I'm going to tell you which page you need to read now. Chapter 4. Chapter 4, I'm not sure which page. I want you to read from equation, from page 93, which is the starting chapter, 93, all the way up to equation 4.1.11. So again, from page 92 all the way to 97. So I'm going to write this on board in a way that in case you forgot it. So we're going to 94, page 94 to the 97. If you do not have a correct page number, this is up to equation 4.1.11. So those are ones which we'll need. So that way we will hurry up the chapter a little bit faster, so that way we won't lag behind. And chapter 4 is about one of the most exciting ones. You've got hydrogen atoms really involved. Now these harmonic oscillators, somehow it's a little bit fictitious, but there you're going to see not fictitious, everything you can measure experimentally. So that's why it's got interested. Okay, again, so these 2 sections you're going to read, and then after that I will tell you you need to submit a report on those ones, so I will give you credit. In case if you do need them, so that this will be on that. Sounds good? Since Toby mentioned you're going to work with me, so that's I work with you now. So these are the ones, the measure that I'm going to do. The reason I'm doing it right now because you have the next week spring break, so that will allow you to have enough time. And when you read and explain it, that's all the key idea that I need. Sounds good? Any other questions? Okay. Make sure you do turn homework today by the end of the day. And any time you need to do today. So, all right, let's going to be stopped here now. So we're going to talk to you guys a week after. I will sign homework today, and I'll let you know which one it is.